Hello, and in this video we're going to look at the deflection of a beam, and in particular we're going to look at the formula to determine the deflection of a cantilever beam that is subjected to a uniform varying load. So we'll begin by looking at the flexural formula, and if I transpose this I get 1 over r is equal to m over ei. If I then look at the radius of curvature formula, if we say that dy dx is very small, so we have a very small number squared, so 1 plus something really, really small is effectively equal to 1, and 1 to the power of 3 over 2 is just 1. So we get 1 over r is equal to d2y dx squared. So if we take this formula here for 1 over r and this one here, and we put them together, we get an expression for d2y dx squared, and that's equal to the bending moment all over E times I. If I want to get dy dx, so dy dx will be the slope of the beam. It'll be the integral of that, and we can see here, if we apply this load, the beam would, bend down like that, and that would be the slope here, theta. So theta is equal to dy dx. If I then integrate that a second time, I will get the deflection y. Okay, so to get the deflection, we need to work out what the bending moment is and then do a double integration. Okay, so if we have a uniform varying load, and if I take any point along the load, so just take this point here, then the value here, this point here, v of x, will be equal to w naught minus w naught over L times x. So w naught over L, that's the slope of the line. So yes, it's just the equation of a straight line, and we can simplify that by taking the w naught out. If I want to get the shear force then of this area, okay, so what's the area under this curve? I would have to integrate that. So the shear force is equal to minus times the integral of v of x dx. And when we do that, we get w naught times x minus x squared over 2L plus some constant of integration a. Okay, so when x is equal to naught then, so we're in at this point here, then the area of this is just the area of a triangle. It's w naught L over 2. So it becomes w naught L over 2. And I'm going to stick that back into my equation, and I have my expression for the shear force. I then want to get the bending moment. So to get the bending moment, you integrate the shear force. And when we integrate the shear force, we get x squared over 2 minus x cubed over 6L minus Lx over 2 plus b. Now, when x is equal to naught, so in at this point here, the bending moment, it's at its maximum. So it will be w naught L squared over 6. Okay, so if I put that expression back in, I have an equation for my bending moment. Okay, so the bending moment at any point along the beam should be equal to this. Okay, so if I take that bending moment and I want to get the deflection, so I need to do a double integral. So I'm going to doubly integrate this equation here. So when I integrate the first time, I'll get dy dx. So this is here, dy dx. And we get x cubed over 6 plus x to the power of 4 over 24L minus Lx squared over 4 plus L squared x all over 6 plus some constant of integration c. Now, at this point in here, when we apply the load, the slope will be 0. So we can say at x is equal to 0, theta is equal to 0. So if theta is equal to 0, then c is equal to 0. So this is my equation for the slope of the beam. If I take that equation and try and simplify it, so I'm going to take the 24L out. So I'll bring that out. I am left with this part of it here. Okay, so this beam, when we apply this load, it's going to deflect, and it'll be at its maximum when x is equal to L. So instead of x here, now I'm going to put in L. So this becomes 4L to the power of 4. This becomes L to the power of 4, and so on. And when we do all that, it simplifies down to theta is equal to minus W naught L cubed over 24 EI. So that is the maximum slope. Okay, the deflection then is the second integral. So I integrate the slope. So this was the equation we had for the slope. That was the equation for the slope. And when I integrate that, that becomes x to the power 4 over 24, x to the 5 over 120 L, x to the 3 all over 12 plus L squared x squared all over 12 plus D. And again, at this point in here, when there is some deflection, the deflection here will be 0. Okay, so if this is an upward load, like in an aircraft, it will deform up, or if it's a downward going load, it'll deform down. Okay, so that distance there, y. So there'll be no deflection here, so D is equal to 0. So when x is equal to 0, D is equal to 0. So there is my expression for the deflection of the beam. So I just want to simplify this by taking the 120L out, bringing that outside. So when I take the 120 and the L out, and I've taken x squared out, I have this equation here. So that is the deflection at any point along the beam. The deflection is at its maximum when x is equal to L. So when I put L in there, I get the deflection is equal to minus W naught L to the power 4 all over 30 EI. Okay, I hope you find that useful.